Hi everybody, we're continuing our conversation with basic chemistry and chemical reactions. If you're following me in the course pack, I'm on pages 17 and 18. We're going to talk about three types of chemical reactions: neutralization, endergonic and exergonic, and metabolic reactions. Alright, so we've talked about acids and bases before. Let me give you a really shortcut way to identify an acid and a base. We know that acids release hydrogens in water, and so they can often be identified by having a hydrogen ion there in the beginning of that chemical compound. Bases can be identified by the hydroxide or hydroxyl ion that's here at the end of their compounds. So when you notice that, that will help you identify the two reactants of this chemical reaction. The reactants are the ingredients that go into this chemical reaction. So an acid and a base are the reactants for neutralization reactions, and the products are what we make. So what we make as a result of this reaction rearranges these molecules and atoms so we produce water and salt. So acid and base combine to form waters and salt molecules. Okay, so some acid-base reactions occur in our body all the time to help maintain a proper blood pH balance. In fact, normal blood pH should be between a very narrow range between 7.35 and 7.45. So we know that buffer systems, like the bicarbonate buffer system shown here, help to maintain blood pH by performing these kinds of acid-base reactions. They bump and nudge the pH back to where it should be in that narrow range between 7.35 and 7.45. Okay, so on the pH scale, that happens to be very slightly alkaline or basic, and we don't want to get too far outside of that range. In fact, if your pH falls below 6.8 or above 8.0, then a person may die from having their pH balance so far out of whack. We know that if you fall below 7.35, we are heading into acid territory, and above 7.45 is alkaline territory. So below 7.35 is known as acidosis, and above 7.45 is known as alkalosis. Okay, so just to take a look at the words here, osis means condition of, we're looking at the condition of the blood. Above 7.45 means the blood is becoming too alkaline. That means there are too many hydroxide ions, and there's not enough hydrogens. If you fall below 7.35, you're now accumulating too many acids. That's too many hydrogen ions. So the body will try to maintain this normal pH range here between 7.35 and 7.4. On average, we're looking at about 7.4 for the overall blood pH. All right, so those are numbers. This here, 7.35 to 45, is a number that I would know for the test. Let me also talk about reactants products once again, and then introduce two new terms, monomers and polymers. Let's start with something we've already discussed. This equation has a yield sign that is pointing toward the right. It is an arrow that always points toward our products. Okay, so these products here on the right-hand side are on the right side of that yield sign. The reactants are the ingredients that go into this chemical reaction. All right, so the reactants lead to the products. You may in fact see chemical reactions that run in the opposite direction. And if that's the case, then you're going to have a reaction run toward the left, and that will be your products on the left at that time. We're not going to do that here in this class, so we're not going to even worry about that. Let's talk about monomers and polymers. Mer is a unit, okay? Mono means how many? That's one. Poly is many. Well, for our conversation, a dimer would be 2. A polymer would technically be 3 or more. So here you have A and B and C. Each are single units, so they would all be considered monomers. A with a single covalent bond joined to B, which is joined to C with a single covalent bond. These are all linked together as a polymer. Okay, so in this reaction, your reactant is a polymer that breaks down into individual monomers, A, B, and C. Those are our products that we make here. Let's now talk about the energy involved in chemical reactions. Energy involvement may lead to an endergonic reaction in which we use ATP, which is energy, to build molecules. So when you're building or growing something in your body, this is an energy input reaction. So it requires the input of energy. Okay, so these reactions are precisely why you have to eat. You have to eat to generate energy to build new muscle and grow new cells. Exergonic, exer means out, right? So these actually produce or release energy. Okay, and these are the types of reactions that involve the breakdown of molecules. So breaking down muscle, destroying cells, losing weight, all are exergonic reactions. So it's easier to make a mess than it is to clean it up. And that's kind of the same concept here. Exergonic reactions release heat. They're involved in breakdown reactions, whereas endergonic reactions are involved in building and the use of energy. Let me also mention this concept here called activation energy. This is the amount of energy required to make a reaction run. Let me imagine that these are two hills, a blue hill and a red hill. I have a 400-pound lead ball and it's my job to push it up and over these hills. Well, obviously if I'm pushing it over the red hill, that requires much more energy on my part. I'd get very tired doing that, pushing a ball of that weight up that hill. The blue hill certainly would be work still, but it's less work than it would be to push it up that other hill. Now enzymes come along and they help to lower the amount of energy required to make a reaction run. So the activation energy, we say, is lowered with the use of an enzyme. So in your body, for instance, if we didn't have enzymes, it would take a lot of energy to make a chemical reaction run, and that may cause your body to use up a lot of energy and generate some heat as a byproduct. So in this reaction here, you can see that the activation energy is lowered with the use of an enzyme. Okay, so that's just a term that we will include in our conversation. Let's talk about chemical reactions related to the parts of your body. In chemistry, they call these reactions combination and decomposition. Here in biology, we talk about anabolism or dehydration synthesis as building or combination reactions. And we talk about catabolic or hydrolysis reactions as decomposition reactions. So let's talk about the word anabolic. Anabolism means to build. So this is a building reaction, okay? We are going to take monomers and join them together to create a polymer. And in doing so, we release water. Water creates stable bonds around those monomers, and we have to drive it off and remove it in order to create a bond between the monomers to create a polymer. All right, so if you think about anabolic steroids, they help build muscle. Anabolic reactions in general help build a polymer. Catabolic reactions are those that break down. Okay, these will take polymers, join and use water to split the bonds apart, and will create individual subunits known as monomers. Let's break down the word dehydration synthesis. If you are dehydrated, we often say that you have lost water. And to synthesize means to make or build something. Well, what we're making or building here happens to be a polymer. So through the loss of water, we can generate or make or build a more complicated molecule. And that's also what we call an anabolic reaction or a combination reaction in chemistry. You can see here that we take monomers. They are known as A, B, and C. We join them together into a polymer here. This is our product. It has got bonds between each of those monomers. Those are single covalent. Okay? And then we, of course, have water as a product. That's because we lost water, dehydration, right? We lost water by driving it away from each of these monomers. It was serving as a protection around those monomers. This is just a more complicated view of what we were just talking about. Here are the water molecules surrounding each one of these that we have to drive off and get rid of. And that allows A to join to B to join to C. Okay, and that's where the water molecules come from. So this is a more complicated view, but it does at least give you an idea of what happens to water when we dehydrate or remove it from these ingredients or reactants that we're using to build a polymer. So let's talk about how this happens. In your body, we actually take glucose and store it as a more complex form called glycogen. Part of that building process involves taking glucose molecules and linking them together. When you store glycogen in your muscles and in your liver, you can later retrieve it to make ATP or energy. So here you can see two glucose molecules being joined together by the removal of, there you go, a water molecule, and it creates a more complicated, more complex polymer. Down here it's known as maltose. That's part of the process of building a more complex molecule we call glycogen. This is a little busy, this picture here. We'll talk more about glucose and maltose in our next PowerPoint when we talk about organic compounds. All right, so the opposite reaction is called a hydrolysis reaction. Let's break that word apart. Hydro means water, and lysis means to split apart or rupture. So literally, we are using water to split and break apart these bonds that hold together the polymer. This type of reaction is also called a catabolic reaction, or in chemistry, it's called a decomposition reaction. Notice what we're doing. We're taking this polymer here. We use water as a jackhammer to break apart the bonds, and we create individual monomers. I call them A, B, and C over here. So here you'll notice in this type of reaction, water is a reactant. By contrast, in dehydration synthesis, where was water? There, it was a product. Again, you can see the more complicated reaction where you take this set of water molecules and we use them and we split them up and put them here. That way we create stable valence shells for those monomers. So water actually has to be in your body to be able to break down these molecules. If you think about this, this is the reason that you have to drink a certain amount of fluid each day. You have to have fluid in your body to help break apart the foods that you eat or to break down worn out cell parts that are recycled and removed. So hydrolysis reactions use a splitting of water to help break polymers down into monomers. This is the exact opposite of a dehydration synthesis reaction. All right, so I'm going to give you a moment to pause this video and look at these 5 examples and figure out what we've got, and then I will help you with the answers. All right, so let's talk about the first one there, soaking dirty dishes in a sink full of water. If you're using water to break apart the food on a dirty dish, you're using it to break down those food molecules. What type do you think this is? Catabolic. So if you've ever let dirty dishes soak overnight in the sink, you are relying on a catabolic or a hydrolysis reaction to occur. All right, the next one is baking a cake. If you've ever put a cake in the oven and you've opened it when it's ready, you've probably been hit in the face with hot steam when you're ready to take that cake out of the oven. That hot steam comes from water being removed or dehydrated from those wet ingredients. Since water is being removed or dehydrated, what type of reaction do you think this is? This one's a building reaction known as an anabolic reaction. All right, the next one looks a little complicated, but I tell you what, there's a really great clue there, and that is the location of water. You'll notice water here is shown as a product, and you also have 2 monomers over here. And of course, when they join, they create sucrose. So this is showing you an example of an anabolic reaction, in other words, a building reaction, or you could call it a dehydration synthesis reaction. So the clue here is looking for where water is located. Now let me caution you, neutralization reactions also have water as a product, so you've got to be mindful of what you're looking at. Let's talk about digesting food. This is a breakdown process. We use water to break the bonds of the food molecules. So what do you think? This one sounds like a catabolic reaction. And then finally, growing something or building something is best classified as an anabolic or a building reaction. I hope these examples help clarify for you some of the differences between anabolism and catabolism. If you have any questions about these, please reach out to me.